I have my conductor again, and I put -5 microcoulombs onto it. So this is a solid spherical conductor. I know the excess charge is all going to be located on the outside here. So if I plotted the center right there, where this is R, the distance from the center, and this is the electric field, the magnitude of the electric field. When I'm outside of this sphere, because of the spherically symmetric charge here, I can treat this like a point charge centered here. So if that's the radius of the sphere, then outside of it, I can treat it like a point charge, and so my electric field is going to be just kq over r squared. So this is some number right here, but the important thing, it's a 1 over r squared relationship, and so it should look like 1 over r squared relationship up to this point right here, and this is going to be the maximum electric field. And so I have -5 microcoulombs there. So this will end up being, this value will be the electrostatic constant times the charge, which I guess I probably should use a capital Q for that, over the radius squared. Inside it is 0. So we have this transition here from some maximum amount to 0. And so what happens? Well, if the maximum amount is, in reality, there are no sharp points. So it's going to transition here. Now from what we draw, it's going to look like a lot like a straight line, but if we zoomed in, what you would have is, in an ideal situation, you have a row of electrons here. You have an electron coming on the outside. Just outside these electrons, we're so close to kq over r squared, and here it is 0. Here the electric field is 0. Here the electric field is approximately k big Q over r squared. And so then it comes down to the transition takes place over what is the size of an electron. Well, we physicists generally consider them point particles, but there is a transition there. And also the electrons are not sitting there just, this like a film. They're moving around a little bit there. And so from a drawing point of view, we would draw it as a straight shot down. In reality, there'd be some curving here and some curving here. Now, if instead of a conductor, I have an insulator. Now, if I put -5 microcoulombs of charge right here and just let it sit, then that is going to, they'll just stay there. It's an insulator. Charges are not going to move easily. So solid sphere, or solid spherical insulator, that's an O right there. And let's say that the total charge on it is -5 microcoulombs. Probably not going to do anything with the number, but just give you some sense. So we start with the insulator, and we evenly distribute the charges throughout. Well, if I'm outside of it, because of the spherical symmetry, I can treat it like a point particle. So if that is the radius of the sphere, outside of it, that's R, and this is my electric field strength. At this point right here, what happens? Well, this is a lot like the gravitational formula. So what I'm going to do is do a little derivation here. Let's start out with, I'm at some distance R inside. Well, all I care about are the charges that are within that radius. The charges outside of this radius R here are not going to have any impact on the electric field inside of that. And so the amount is inside there, so I know that the total volume of the entire sphere, I'll just put a little subscript capital R here to represent the entire sphere, so that's capital R, is 4/3 pi r cubed. The volume of the smaller sphere, so lowercase r, is 4/3 pi r cubed. If they are evenly distributed, that means that the charge density is the same, so rho, which is equal to charge over a volume, will be the same. So big R, and then Q, little r, v little r. In other words, the charge that is within inside that is just the total charge divided by the ratio of these two things, which is little r cubed over big R cubed. And so therefore, the electric field caused by the charge within the small radius here is kq within the little r over r cubed. Oops, sorry, over r squared. I don't know where that r cubed came from. Which is k big Q little r cubed over big R cubed and then r squared. The r squared cancels out with two of those, and I'm left with kq over big R cubed, perhaps that's where it came from, times r. So this is a constant. K is the Coulomb's constant, or electrostatic constant. Big Q is the total charge we stick on here, -5 microcoulombs. Big R cubed, big R is the radius of the entire sphere, but as we get inside there, this little r goes to 0. In other words, this is a linear relationship. And again, there's going to be some transition there. It should not be a sharp point, but it's going to be, in essence, this is pretty much what it looks like. This is linear, and this is a 1 over r squared relationship.